All right, so moving on to Unit 5, but we don't have to give up trig quite yet. We got a whole other unit on trigonometry. And if you like graphing, this is not the unit for you. There's no graphing. So it's all algebra, all formulaic, all numerical, all that stuff. The one thing that does overlap from last unit is that unit circle is still going to be very applicable. Okay? So knowing those exact values are going to come out multiple times. What this unit is, it's now going into the more algebraic side, and that is being able to simplify expressions that have trigonometric parts to them, as well as solving trigonometric equations. This is the algebraic portion of the trig part of the course. So there are 6 sections. You might notice that the package I gave you isn't as thick as past lessons. Like last unit was a bit thicker because we had all those graphs to do. So this one's not as big. I do all the essential examples you need for each section here, but I don't overdo it. It's really up to you to do the practice for this unit. If you do the practice, this should be a unit that's very predictable, and as long as you know what strategies in what situation, it's a very numerical algebraic unit that you should be able to be successful on. But the one thing that students kind of, it's your comfort level with the identities from last year. Putting out show of hands, like how many of you guys liked the identity, like this proving identity stuff? Well, that's good. Okay, so that's good because we just basically do that times 1,000. Like we're going to do that plus more. So a lot more of that stuff. Instead of just one lesson, it's like half the unit is that stuff. So let's start with some basic ideas, basic identities. So it's important to be able to recognize when 2 trigonometric expressions or functions are equivalent. We call these equivalent expressions identities. Your goal is to always convert a trigonometric expression to its simplest equivalent form. And here are some facts you need to know. So this first section is going through some minor rules, but still important rules. And again, the ultimate goal is to take something that's not as simplified as it can be and get it to be as simplified as it can be. So we're going to go through 5 rules, and these are the rules that are going to help you answer the 7.1 homework. So, rule number 1. You can create an equivalent trigonometric expression by adding or subtracting the period of a function. So, from chapter 6, or the last unit, unit 4, the functions y equals sine x, y equals cosine x, y equals cosecant x, and y equals secant x all had a period of what? 2 pi. Okay? And then the functions y equals tan x and y equals cotan x had a period of pi. So if you add the period or an integer multiple of the period to the value of x, the value of the function will be the same. This also applies to subtracting the period or an integer multiple of the period. So here's the visual. You don't have to draw this, but I just want you to have the visual, right? So here's the graph of sine x, right? So what this is saying is, if I pick points on this function, y equals sine x, and let's say I move them all 2 pi to the right, which is what this is saying, right? Whenever you see inside the brackets a plus the angle or minus angle, it's a horizontal translation. What happens if I take this point and move it 2 pi to the left? Where would this point end up? Right here, right? Where would this max end up? Right there. Where would this 0 end up? Right there. So you guys get that a horizontal shift of a period doesn't actually change your function. It goes on top of itself. Does that make sense? So it's literally the same function. Because if this function goes for x element reals and I shift that function that goes for everything 2 pi left or 2 pi right or 4 pi left or 4 pi right or 100 pi left, 100 pi right, it doesn't matter. It will always be the same function because you're shifting right on top of itself. There's no change. So if you ever see a sine function with x plus 2 pi or x minus 2 pi, you can just say, well, that's just the same thing as the original function sine x. You don't have to shift it at all because a shifting of 2 pi doesn't change the function. Does that make sense, everybody? So for cosine, I could go to the right it would be the same deal if I shift, you know, again, if I shift cosine, right? Remember, we only draw little pieces. Remember, these functions go on and on. If you have a cycle of cosine, and I shift that function, you know, 2 pi to the left, so if this is at 2 pi, and then I say, hey, I'm going to shift this piece 2 pi to the right. Okay, approximately, right? So it goes right on top of itself, and therefore is not really a change. So cos of x minus 2 pi is just cos x. So for sine, cosine, secant, and cosecant, it has to be a multiple of 2 pi, so all the even pi's would work. But for tan and cotan, what was the difference, guys? The period was just pi, so you don't have to, it can be any a multiple of pi, including odd pi's, you will get tan x. Does that make sense? Because with that one, remember, for tan x, right, I could take this piece here, right, and say, I'm just going to move it pi to the left, or pi right, pi left, and I'll be on top of the next little tan cycle, right? So therefore, you only have to go pi. So everyone cool with that? But you guys get 2 pi would be fine. Just means you take the one over here and go 2 pi over, I'd still be on top of a cycle of tan. So easy rule number 1. If, again, what's the goal of this, guys? Is if you see a left side, you can replace it with a right side, the right side always being simpler. Does that make sense, what I just said? That's your ultimate goal, is make things as simple as possible. Eventually, you might see an expression that looks like this. Don't have to write it, but this could be coming up at some point. If I see this, we now know, oh, I can replace this first one. I add 2 pi, oh, that doesn't change it. That's just the same thing as sine x. And then this is where, hopefully, remembering you're simplifying identities, your goal is to find a whole bunch of these common pieces so that you can, right? That's the ultimate goal, usually when we simplify, right? Is to get things as simple as possible. But showing that, knowing that rule allows you to do that replacement. Yeah. Any questions? Okay. So let's move on to rule number 2. Okay. So you can create an equivalent trigonometric expression using its symmetry, odd or even. You guys remember way back first week of the course, we talked about symmetry as a characteristic of a function. And I just said, hey, trig functions are coming up later, but you should just know these rules. Do you remember that? Like, I made you memorize a rule for cos and for sine, right? Based on the symmetry of those two graphs, right? So again, how would you describe the symmetry of cosine, guys? Versus the symmetry of sine? What's the symmetry rules? A function has even symmetry if the graph reflection in the y-axis. If I can take numbers for negative x and they go right on top, if I flip it, if I flip it this way, I can't really show the flip, okay, so they could flip it across, and it's a perfect match, okay? Obviously that doesn't work over here, right? I can't go flip, it doesn't work for sine, right? Sine, the flip in y-axis, it's not even, or else the graph would look like that, with the green part with the blue part. So this one has odd symmetry. Remember the definition of odd symmetry, the double flip, right? So a max here would go flip, flip, double, you have to go 2 points, so it's a reflection about the origin. Okay, so the idea here is the symmetry here, you can do a rewrite, so because we don't want the negative in the brackets, we'd rather have sine x or cos x and then a negative outside. Because then, again, what's the purpose of that? Because then I can cancel out common sine x's. I can't cancel out a sine negative x with a sine x. They're not identical. Okay, so the rule is, let's talk about the symmetry. So we know that cosine was even. What do you think any other of the 6 are also have even symmetry? Do any of the 6 have even? If cosine has even, let's think logic. If cosine is even symmetry, not inverse, reciprocal. The reciprocal of cosine. Again, I'll just draw it in the spaces here, guys? Do we agree, like, that's what cosecant looks like, right? I'm gonna take away the blue, right? Right, so there's secant. So secant, we agree, even symmetry, reflection about the y-axis. So we know sine x is odd symmetry, and therefore y equals cosecant x will also have odd symmetry. What do you think about tan?
No symmetry.
A point here.
Inverse? Or no?
Point here. I know this. Okay, let me see if I can do this. Point here. This is way far away, so you guys gotta go like wah wah, like over here. So it's like the farthest away will be a double reflection. So it's odd. So tan x also has odd symmetry. Okay. So tan x has odd, so cotan x is also odd. So that's the moral of the story here. So y equals tan x. And so the rule is, how do we turn that rule into an algebraic rule? Well, it's all about the fact that if I put negative x in, it's equivalent to, if you remember, negative sine x. Again, refresh your memory again of the rule. Okay, so I pick a point here, let's say like a negative pi over 2. Agree, sine of negative pi over 2 will be negative 1. I want you to say, well, what's happening at the positive version? It's 1. How do I make those two things equal? I put a negative in front, and now I make this number negative, and then it's equal. So for an odd symmetry function, the algebraic version is you get rid of the negative inside, but it comes on the outside. For even symmetry, it's a direct relationship. Like 1 would match with 1, 0 would match, well, 0 always matches with 0. 1 matches with 1, like whatever, like root 3 over 2 over here would be a root 3 over 2 over there. Everything would match perfectly. So this is one where the negative just goes away because it's equivalent. Does that make sense, everybody? So I go for cosine. I don't know how many times I draw this in this lesson, but there's cosine again. So I pick a point over here. I go to its perfect match over here. It's always the same. I go to this point over here. I go to this point over here. It's same. Go this point over here. This point over here. Same. So it's always the same. I don't have to do any adjustment. So I don't have to make it negative. So it's just equal. For tan, it's because it has odd symmetry. It will be like sine. So it'll be negative tan x. And all the reciprocal functions will have the same rules. So if you wanted to put underneath cosecant negative x will be negative cosecant x. Secant of negative x equals secant x, and cotan of negative x will be negative cotan x. Check on the student outside. So, rule number 3. So, for this rule, we're going to do a little kind of mini investigation, just to make sure we're on the same. We know how this rule kind of comes about. So, you can create an equivalent trigonometric expression using complementary angles. Have you heard of complementary angles before? I don't mean angles that say, wow, you look lovely today. Okay. So do you guys remember the mathematical definition of complementary? The last time you saw it probably was grade 9.
Like what it pattern?
No, it's not Z pattern.
Like what it's like, oh, I don't know.
Does that ring a bell? What would be in grade 9, what's the rule if you saw something like this? X plus y equals
90.
complementary angles add to 90 degrees. Complementary angles add to 90 degrees. In radians, that means complementary angles add to pi over 2. So what I'd like you to do to warm up for this, to see what this rule does, let's fill in all of the exact values for these 12 trig ratios. All of these are of the special angles pi over 6 and pi over 3. So you shouldn't even need your unit circle anymore. Your unit circle should be right in your brain. Let's see. At pi over 6, so I used to have I was telling you period 1, I used to have when I was taught this in high school, I had a math teacher who would like be spinning her arms around like this to like for the different parts of the unit circle. So if 0's over here, pi over 6 is just the little angle up here. Who's that? Oh, okay. She's leaving? Okay, she needs to sign out officially.
She's with Mr. Devon. I think you called.
Oh, okay. Okay. Okay, so pi over 6. Okay, so for pi over 6, we've got what are the values of sine pi over 6 and cos pi over 6. So cos pi over 6, let's start with sine. Sine pi over 6 is half. Good. Cos pi over 6. Good. And tan is going to be sine over cosine or simplified. Yeah, root 3 over 3. And then cosecant, secant, and cotangent of those three of the is just going to be the reciprocals of what you just wrote. So what are the reciprocals? We've got
2 root 3 over 3 and 3.
good. For sine of pi over 3, now we're at this location, right? Versus this location, right? And so if you're at this location, you want to draw the little picture to help you, you can. So at this location, what do we got? So sine of pi over 3 is cosine of pi over 3, tan of pi over 3, reciprocal, reciprocal, reciprocal. 2 root 3 over 3, 2. Okay. Okay. Did you sign in, sir? For being late? Sign in? Paper?
No.
You have to go sign in if you're late, right? This is set. Okay. Maybe walk around this way again. Okay. So the idea here is that, hopefully you noticed, and you probably noticed this up to this point, that there's all the numbers for the pi over 6, all the different values are all found over here at pi over 3, just at different locations. Agreed? Like all the numbers over here are equal to one of the places over here. But let's actually match them up. Let's play a matching game. So sine of pi over 6 is a half. What does it match up to? Cosine of pi over 3. Okay? Those are equivalent. Let's work across. Cosine of pi over 6, what's it equivalent to? Cosine pi over 6 matches up to? Here's what I'm doing, guys. Cosine pi over 6 is root 3 over 2. I go over here, where's the root 3 over 2? Sine pi over 3. So that's the match. So that's my match. Sine of pi over 3. Let's kind of do a U shape going this way. So let's go to tan next. Tan of pi over 6. Tan of pi over 6 is here. It matches up to cotan of pi over 3. Okay, cosecant of pi, oh, no, it's actually, I want to go down. So let's do cotan pi over 6. Cotan pi over 6 is here. Cotan matches up to tan pi over 3. Secant pi over 6. Secant pi over 6 matches up to cosecant pi over 3. And cosecant pi over 6, what's left? Secant. So does everyone get each of the numbers in the left match up with one of the locations on the right? Now, funnily enough, or maybe not so funnily enough, pi over 6 and pi over 3 are complementary. Because remember what degree-wise, pi over 6 corresponded to what angle in degrees? Pi over 6 was 30 degrees, and pi over 3 was 60 degrees. So, and again, just to confirm, so pi over 6, if I add these two angles together, Got a common denominator. Right? You get pi over 2, right? If you add pi over 3 plus pi over 6, you get pi over 2.
Reminder to teachers, please send down your period 4 and all outstanding attendance. Thank you.
Okay, so now that we have this rule, let's see if we can kind of come up with an idea of what matches what. So sine matched up to cosine. Tangent matched up to cotangent. Secant matched up to cosecant. Agreed? So guess what? There's the complementary angles will match up with co-functions. And what I mean by co-functions, we never really talked about the names of the trig ratios. You just learned SOHCAHTOA and you just like embraced it in grade 10. But sine, cosine, sine and cosine are related by their complementary angles. Okay? Secant, cosecant, cotangent, cotangent. For complementary angles, the values will be the same. Does everyone follow what I just said there? I'll say it again. For complementary angles, the values of sine and cosine will be the same. So if I know an angle, pi over 6, and I know the value of sine of pi over 6, I know that the co-function cosine of its complement, pi over 3, will be equal. And that works for all 100% of the time. So these are the general rules here. That if you have, first of all, do you all agree, if x is an acute angle, pi over 2 minus x will be the complement of x. I'm going to write something here just to kind of make sure we're all on board. Okay, here's unit circle, here's x, and here's y. Do you agree x plus y on the unit circle would be pi over 2? If you isolate y here, what would you get?
Pi over 2 minus x.
Does everyone understand that it might look confusing, but we don't want to introduce another variable? So anytime you see pi over 2 minus x, it's the complement of x, the complementary angle with x. So if x is pi over 6, pi over 2 minus pi over 6 will be pi over 3. Okay? Whatever x is, pi over 2 minus x will be its complement. So the key here is I can take all of these little bit more complicated expressions and turn them into simpler expressions using the co-function. So the way you do this is, what's the co-function of sine? Just think of their names. The co-function of sine is cosine. And then you need the complementary angle to pi over 2 minus x. Well, that's just going to be x. Does that make sense? X plus pi over 2 minus x is pi over 2. Is this making sense? No? Okay, let me try again. Let's do an example. So here's pi over 6. Here's pi over, and this would be pi over 3 over here. Let's just go with that. So, and again, normally we don't do this, but let's just kind of say, well, that's not really the way we should do it. All right. Ugh, okay, let me try that again. So here's my unit circle, or corner of the unit circle. Here's pi over 6. And it has root 3 over 2 half. Here's pi over 3, right? Half root 3 over 2. Okay? But do you guys get that pi over, so if I said, let's say pi over 2 minus pi over 6 would be pi over 3. Again, I could go 3 pi over 6 minus pi over 6 is 2 pi over 6, which is pi over 3. So we're all happy that pi over 3 and pi over 6 are complementary. So the value of sine pi over 6 equals the value of cosine pi over 3. Okay? So I just pick the co-function name, and then I pick the complementary angle. The complementary angle to pi over 2 minus x is just x. Yeah, they cancel out. It's like x plus pi over 2 minus x would be pi over 2. Does that make it more? I know it's a little weird talking in general, but remember, if this is a number, then this is another number. The two numbers add up to pi over 2. X can be any number. We want to talk in general. We don't want to be specific. We want to be general. Okay? So I'm going to erase all this because I just wanted to clean it up. So that right now, I want the main idea here, guys, is do we agree that the left side's more complicated than the right side? Our goal is to turn things into simpler forms. So I can replace sine of a complementary angle equal to cosine of the complement. Cos of pi over 2 minus x is going to be the reverse, so I pick the co-function of cosine, which is sine. I pick the complementary angle to pi over 2 minus x, which is just x. Tan of pi over 2 minus x, I need the co-function of tan. Cotan, I need the complementary angle to pi over 2 minus x, which is just x. Cotangent of pi over 2 minus x, I need the co-function of cotangent. And then the complement of pi over 2 minus x, x. Secant of pi over 2 minus x, I need the co-function of secant. Cosecant, complementary angle of pi over 2 minus x, x. And then finally, co-function of cosecant is secant, complementary angle x. Before we end this part of the lesson, we're going to do an example that's numerical. But the idea is, if I tell you to find an equivalent expression to something like the left side, you just pick co-function, and then you pick co-function, and then you pick the complementary angle. So I'm going to write something here, because I can't remember why I don't write it down, but I'm just going to write co-function identities. That's what these are. So you know the paper I gave you that has all the rules on it, the expanded list of formulas, the co-function identities are there. Okay, it's part of the package of identities that are on the sheet. Okay, and you'll see a little, again, as you do the homework for this, you'll get a little bit more comfortable with this. Okay, rule 4 is a rule that you've already had a little bit of a taste of. You can create an equivalent trigonometric expression using the related acute angle. There's one question on the test like this, right? Using the related acute, write an expression in terms of related acute angle. So the idea here is, think of x being an angle in quadrant 1. So here's x in quadrant 1. You guys get that in the other 4 quadrants, there's going to be mirror images of that x. That was not really a good mirror image, but okay. So there's my, that's horrible. Let me try it again. I'm going to erase that one. Let me try it, make it actually match. Okay. If we're on a circle, and I tried my best to draw these 4 terminal arms so that they're all a mirror image of the same angle x. Do you agree that there's an angle x in every one of these, right? In quadrant 1, the angle is acute. But in the other 4 quadrants, like for quadrant 2, there's my angle. Okay, in quadrant 3, here's my angle. In quadrant 4, here's my angle. All of those are the angles in standard position, but what's the little bit extra piece in each of those that's going to be consistent with quadrant 1? The related acute angle, right? Do each of those angles, the purple, red, and green, do they all have a related acute angle in them? In the green one, it's here, right? In the red one, it's here, and in the purple one, it's here, right? And so it's always made with the x-axis. So the idea is, if you want to write each of these expressions in terms of the related acute angle, it's all about using cast rule. This might look confusing in general, so let me put it to you another way. This should be familiar to you from okay, I'm not just picking these numbers out of a hat. Do we all agree that what I've just picked are 3 angles in quadrants 2, 3, and 4 that are all have what as the related acute angle? Pi over 6. So can I write each of these? I'm not saying these are all correct, but can I write it? Each of these at least is partially correct right now. but only one of these is actually correct right now. Out of the three, which one is the one that's actually correct right now, out of the three? The 5 pi over 6, because what's true about 5 pi over 6 versus 7 pi over 6 and 11 pi over 6? Quadrant 2, and in quadrant 2 sine is? So how can I fix the other two? Okay, now here's the idea, guys. In each of these cases, let's think about 5 pi over 6. Isn't that pi minus pi over 6? Isn't 7 pi over 6 pi plus pi over 6? And isn't 11 pi over 6 2 pi minus pi over 6? So you get what I'm saying, that this is your general form. If you know the related acute angle, these are the matching angles in quadrants 2, 3, and 4 in general, for any angle x. Right? If I have an acute angle x, if I want its corresponding obtuse angle in quadrant 2, I'm going to subtract it from pi. If I want its corresponding angle in quadrant 3, I'm going to add it to pi. If I want its corresponding angle in quadrant 4, I'm going to subtract it from 2 pi. All of these expressions we can write in terms of the acute angle by using the x. So I'm going to write sine x, cos x, tan x, but only one of these will be positive, the other two will be negative based on the cast rule. This is our quadrant 2 list. In quadrant 2, which is the ratio that's positive, sine, so what should I put next to cos and tan? Negatives. For sine of pi plus x, cos of pi plus x, tan of pi plus x, I'm in quadrant 3. Again, it's going to be sine x, cos x, tan x again, but this time which one's the one that's positive? Tan's positive in quadrant 3, I need negatives in front of sine and cos. For quadrant 4, again, it's the same answers, sine x, cos x, and tan x, but this time which one's the positive one? Cos, so these two are my negatives. So again, why would this be useful? Because if I said, just again to give an example, if I said simplify we all agree that's disgusting looking right now. Yeah? It's not very nice looking again. But do I have a replacement for each of these that I could go to my chart and go, okay, pi minus x. I can replace sine of pi minus x because x is acute in my mind. So if x is acute, this is a quadrant 2. In quadrant 2, sine is, so this is equivalent to just positive sine x. It's making sense. Tan of pi plus x in quadrant 3, tan is positive, and so tan of pi plus x is just tan x. In quadrant 4, what's happening with cosine in quadrant 4? It's also positive. Look what you've done. You turned this into a nice cleaner version, and if I had thought this through a little bit harder, I might have put the cos there and the sine there, but just to refresh my memory, do you guys remember what sine x, working a little bit ahead, remember what sine x over cos x is? Yeah. So, you could write it like this. Ooh. You remember this fun stuff? If you multiply tan x by itself, you put the squared on the tan, just so you don't confuse it with the squared on the angle. But again, this isn't going to show up in the homework at all, but I'm just trying to get at the fact that I turned something that had ugly angles that weren't simplified into something that could be simplified, and then canceled out if necessary. Okay? So, moral of story, that's using, in terms of the related acute angle. So anytime they're referring to write an expression in terms of related acute angle, they want you to use this rule. And again, we're going to do an example before the end of this so you know how to do the homework. Okay, last rule is the fact that you can create an equivalent trig expression using a phase shift. Remember, phase shift is just the trigonometric way of saying a horizontal translation. The graphs of y equals sine x and y equals cosine x, and correspondingly y equals cosecant x and y equals secant x, are a phase shift of blank apart. So just because I'm not done with graphing, so here's a graph of sine. Okay, if I graph the corresponding cosine, not perfect, but okay. So if I take a look at blue versus green. Okay, blue is sine, green is cosine. Do we agree that they're a shift apart of each other? Right? How far is the shift? Like how far apart is one from the other? So 2 pi's here, pi's here. How far do I shift? Right now, this green dot, I'm going to just make it a dot. This green dot right here is at. Okay, sorry guys, just give me a second. I'm just going to trace over it in red all at once so that it reads it. Okay, red graph. If I shift it over, I want to know how far I shifted over to get to there, right? Max to max, like this max to that max. Where is that max on sine? So it's a shift of pi over 2. Okay? So sine and cosine are just a shift of pi over 2 apart. So if I start with the graph of sine, so if I start with the blue graph, if I want blue to go on top of red or blue to go on top of green, do I shift right or left? Left. So I need to go left. How do we show left in terms of a transformation? It's going to be x. The plus, minus, negative, but plus. Yeah, plus pi over 2. Whereas if I want to shift cosine onto sine, I'm going to shift right, and therefore would be, well, the shift is positive, but in the formula it's x minus pi over 2. So again, if I see x plus pi over 2 inside, I can say sine of that is equal to cosine of just x, or cos of x minus pi over 2 is sine. A lot of people get this one mixed up with the co-functions, but there is a big difference. They both have pi over 2's, but I'm just going to flip back. Do you guys see a difference in the way the formula is set up for co-functions? Look at the co-functions. Pi over 2's first, and you're always subtracting. Pi over 2 minus, pi over 2 minus, pi over 2 minus. What do you notice here? The pi over 2's last, and the x is always positive. So that's your clue which one you're looking at, which rule you're applying. Yeah. Okay, so here's the important stuff. So this is the type of question, all of this work, there's actually not a lot of homework with this section. Okay, I just went through a lot of things. Just more practicing your knowledge of these 5 rules. But if anything's the most important, it's example 1 and 2 I'm about to show you right now. So example 1 says, use the co-function identities to write an expression that is equivalent to each of the following expressions. Co-function identity, so if you ask for co-function, that's where you're using complementary angles. So you see co-function, and your brain will go complementary, co-function, complementary. So I see cosine of 3 pi over 8. Your answer will be the co-function of cosine and the complementary angle of 3 pi over 8. You put those 2 pieces together, you're done. Okay? What's the co-function of cosine? Good. You just got half a mark from me. Congratulations. Okay, now I want the correct angle. I need the complementary angle of 3 pi over 8. How do we find complementary angles? What's the rule for degrees? If this was cosine of 10 degrees, you would go 90 minus 10. Well, what are you going to do for radians? Pi over 2 minus 3 pi over 8. Pi over 2 minus 3 pi over 8. Okay? So pi over 2 minus 3 pi over 8. In period 1, they're like, yay, calculator. And I went, boo, you shouldn't need a calculator for this. Okay? Can you get a common denominator there? 8. What's pi over 2 if you write it with an 8 denominator? The numerator would be minus 3 pi. That's all I need to really see as your rough work. Do you now know the complementary angle to 3 pi over 8? Yeah, you don't put the 1, but yeah, pi over 8. You're done. Question answered correct. Do you get what just happened there, guys? I want you to understand something. We've been focusing on the pi over 3 and pi over 6 so much. just because it's not pi over 3 and pi over 6, you guys get, there's this like really wimpy angle over here that happens to be a pi over 8 angle. It has a point. Okay, blah, blah. Okay, whatever. Okay, maybe I won't pick that one. I'll pick AB. Okay, you guys get its complementary angle, okay, it's going to be this, whatever this size is, it's going to be that same size here. You guys get what I'm saying? So the matching angle here is the complement of pi over 8. That's your 3 pi over 8, is this red angle here. The green angle here is the extra pi over 8. Is this making sense? Because 3 pi over 8 plus pi over 8 will be 4 pi over 8. There's your pi over 2. But what do you think is the coordinates of this point right here, guys? If this is A comma B, what's happening up here? Exactly, because it's a circle and everything's nicely symmetrical. So it's the same distance here, so it's the same distance away from the 1, 0 over here. It's going to be the same distance away from the 0, 1 over here. It's all, everything kind of matches up. Is this making sense? Okay? And so what you've just done is you said, I picked the complementary angle and I picked the complementary place. So if I wanted cosine here, I need the sine of this one. Make sense? Okay. All right. Let's try the next one. You don't have to draw this every time, but I just want to show you visually what's happened. So now, again, hopefully just get in the zone of this where it's going to be write the cofunction, write the complementary angle next. Write the cofunction, write the complementary angle next. So cofunction of tangent. Correct. Now I need the complementary angle of 7 pi over 20. Pi over 2 minus 7 pi over 20. So complementary angle, so I get my common denominator. This time it's going to be, what's pi over 2 become? 10 pi over 20 minus 7 pi over 20 becomes? 3 pi over 20. And done. That's equivalent. Next. Does this make sense? It's not as hard as it seems. That's like the ultimate goal. It's like once you get into the habit of it, it's not as hard as it seems. Secant of 2 pi over 5. Oh, I plugged in. What? Plug. So secant of 2 pi over 5. So again, cofunction of secant. Correct. Complementary angle. So over 5. This time, and you'll notice this up whenever the denominator's odd, you guys you're going to have to do a double adjustment. Even if you don't have to, you only have to adjust the pi over 2, but here you guys we have to adjust both. What would be the common denominator with 2 and 5? So the pi over 2 would become, and the 2 pi over 5 would become, and so results in the secant pi. Correct. Equivalent. Done. Moving on. Okay? Any questions? So anytime you see cofunction, you write the correct cofunction trig ratio, and then just pick the complementary angle. It's always equivalent. Worst case scenario, you're not 100%. If you have your calculator and you're in radian mode and you do cosine 3 pi over 8 gross decimal number, and you do sine of pi over 8, you should get the same gross decimal number. Okay? Same number each way. Okay, the other type of question, this is literally taken right off of your test. Write an expression that's equivalent to each of the following using the related acute angle. So the only difference is you have to be careful when it's not a special angle, you have to be careful that you choose the correct acute angle. Let's start with the easy one, because 5 pi over 3, do we know what the related acute angle to 5 pi over 3 is? Yeah. 5 pi over 3 is special, right? What's its corresponding angle in quadrant 1? It's just pi over 3. So here's the nice thing about related acute angle. You just pick the same ratio, so copy tan to tan. I put the related acute angle in here, in this case pi over 3. And now the only question is, do I need a negative or not? So it's a 3-part process.
Good afternoon, residents. Please pay attention to the following announcement. There will be a brief key club meeting today after school in the cafeteria. Continuing this week and throughout November, the library will be open during periods 3A and 3B. It will be closed during period 3C. The library club will meet briefly right after school this Wednesday, November 21st. Attention all students who are writing the University of Waterloo Math Contest
No.
Okay, and please, prayer ministry is canceled tomorrow, Wednesday, due to a short day for our mission. Thank you for listening to the end of the day announcement, and I hope you have a great rest of your day.
Okay, so right now, if I move on to B, am I going to get full marks for A? Because the problem is you have to, what's the third piece? This is a three-part process. First part's super easy. Copy the ratio. Tan, copy tan. Second step, you need the related acute angle. So you need to find the angle that 5 pi over 3 makes with the x-axis. Does that make sense? So we know 5 pi over 3 is down here, right guys? We need the related acute angle that's going to match up to the quadrant 1 angle here. What is it? It's pi over 3. So part 2 done. Now part 3 is, at my angle, the 5 pi over 3 is a quadrant 4 angle. In quadrant 4, tan is negative. So right now, I'm saying a negative number equals a positive number. That's not true. How do I make it true? Put a negative in front. Now it's true. Everyone good?
Yep.
Okay, let's try the next one. Now, it gets a little trickier because now they're not going to be special angles anymore, but you can still do this. Cosecant of 9 pi over 8. Let's do the easy part. Copy the trig ratio. Cosecant. Yay! Okay. Now, I need the related acute angle. 9 pi over 8. I'm not familiar with this. This is what your brain should go to. Is 9 pi over 8 closer to pi or closer to 2 pi? Pi. Again, I want you to think of it like this. Can you write pi so that it's over 8? How could you write pi so that it's something over 8? It would be 8 pi over 8. Why is that going to help you? Because now you have a reference that right here, this is 8 pi over 8. If you go to halfway around the circle, right? You're around the unit circle, halfway, right here, you've gone 8 pi over 8 radians. Where's 9 pi over 8 going to be, guys? A little extra bit into quadrant 3, right? How much of an extra bit? A pi over 8 extra. Because 8 pi over 8 plus another pi over 8 would be your 9 pi over 8. So I'm a little bit higher than pi. I'm a little bit into quadrant 3. So I know what my related acute angle is now. It's the angle that the green term line makes with the axis. Well, I know it's an extra pi over 8. But now the question is, do I need the negative or not? Cosecant is related to its reciprocal. What's the reciprocal of cosecant? Sine. In quadrant 3, sine is negative. So do I need a negative or am I good? You need a negative and you're good. Okay. Sine of 11 pi over 14. So do the same argument, guys. 11 pi over 14, is that closer to pi or 2 pi? Pi. So write pi so that it's over 14. So what would it be? Pi is what over 14? 14 pi over 14 is right here. 14 pi over 14. Wait, 11 pi over 14. So what quadrant should my terminal arm be if my angle goes to 11 pi over 14? It's in here, right? So this angle here is 11 pi over 14. Does that make sense, everybody? What's the extra bit? What's the related acute angle right here? How much extra would I need to get to pi? 3 pi over 14, right? 11 pi over 14 plus 3 pi over 14 would be 14 pi over 14. So, again, pi minus 11 pi over 14, 14 pi over 14 minus 11 pi over 14 is 2 pi over 14. I don't need to see this. You can do this in your head, but I now know 3 pi over 14 is the related acute angle to 11 pi over 14. And my question to you is, do I need the negative here or not?
No.
Because in quadrant 2, sine is, and so I'm good to go. And just to finish this off, if you can squeeze this in, you can. what if I gave you cosecant of, um, 60 pi over 31. So this time, is 60 pi over 31, is that closer to pi or to 2 pi? 2 pi. Because here's what you should do. Go to the denominator 31. What's double that? So do you guys get pi is going to be 2 pi is going to be 62 pi over 31. As soon as you identify that, do you know what the related acute angle is? Because if your angle goes to 60 pi over 31 and 2 pi all the way through is 62 pi over 31, what's the related acute angle? 2 pi over 31, right? The extra bit. So the cosine of 2 pi over 31, and then do I need the negative or not? Where's 60 pi over 31? It's in quadrant, and in quadrant 4 cosine is positive, so I don't need the negative. So that's your thought process when you do this. Okay? Okay. So I'm going to still do the little intro to the next lesson, just to get it into your minds of where you're going. And for those of you that are a little adventurous, you can give 7.2 a try tomorrow. But for sure, 7.1 needs to get done over the next 2 days before I see you on Thursday. Okay? So the next lesson we're doing is called compound angles formulas, compound angle formulas. So the idea here is that we never dealt with this in grade 11, the fact that the angle in the expression might not be a single angle. So a definition of a compound angle is an angle created by adding or subtracting two other angles. So sometimes you're going to get an expression in the angle. Last year, if you go to your sheet that I gave you, the formula sheet, do you guys get the top two headings? Those are your identities from grade 11. Okay, the top two headings, right? You had the reciprocal identities, the quotient identities, the Pythagorean identities, that was it. Do you guys get that no matter what, if you pick the left or the right, the angles were the same on each side. Theta or theta, x or x, it was the same. Okay, nothing changed. We want to expand our knowledge. What if the angle is made up of the sum or difference of two other angles? And there are some rules for that. So the first type is the compound angle rules, okay, or compound angle formulas. So you will be provided with this formula sheet. You are provided with this formula sheet for the test. You will be provided with this formula sheet for the exam. Okay? But for your own well-being in terms of just knowledge for the future, I would recommend you memorize these and use the formula sheet just as a double check to make sure you memorized it correctly or using it correctly. On the AP exam, they will not provide you with any of these, but they do tend to crop up here and there in a couple, like in one random multiple choice, you might have to know an identity to be able to do it. So it's important to know the rules. So all I'm going to do is run through this, and then we'll start doing the examples on Thursday, but just so you can kind of get a feel for how the formulas work. So if I have sine of a sum of two angles, the formula, if you look at it for sine, it alternates. It starts with the same ratio, sine, and I want you to notice something. No matter which formula we're doing, the angle order stays the same. So whatever the first angle is will come in the first part of every piece. The second angle will always come second. So sine of A plus B becomes sine A cos B plus cos A sine B. So this starts with the sine, but it alternates. So it goes sine A cos B plus, and then it's the reverse cos A sine B. The order of the angle stays the same. It's just the reverse of the ratios. For the subtraction, it's the exact same formula except with a minus sign. Okay? Memory device for sine is same signs for sine. Same sign. So a plus in the bracket is a plus here. A minus in the bracket is a minus here. So same signs for sine. The reason why that's going to help you, because the second one is super cheesy, my memory device. Okay? So for cosine, first of all, notice it doesn't switch. It's cos, cos, and then sine, sine. and the sign switches. So cos of A plus B is cos A cos B minus sin A sin B. Cos of A minus B is cos A cos B plus sin A sin B. So what's the little memory device you could think of here? If you have cos, 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 sine switch, sounds like couscous sandwich. So couscous sandwich, cos, cos, sine switch. Couscous sandwich, cos, cos, sine switch. So that's a way to think of it. So if you see cosine of a sum, you know, okay, I'm going to go cos, cos. I know cos comes first, and then I switch the sign, and then after cos, cos has to come sine, sine. Does that make sense? And again, if you remember that one, it's easier to remember the first one because it's not cos, cos, it's sine, cos. Like it'll be the alternating one. Yeah, cos, cos. If you want to remember cos, cos, sine, sine, sine switch, like however you remember, the key thing is the sign does switch, and it's a different formula, right? Different ratio, different formula. For tan, so you have tan of a sum or tan of a difference. Again, the formula is the same for plus and minus. The only difference is where the signs are, right? So it's tan A plus tan B all over 1 minus tan A tan B. The exact same form, except the minus is on the top of the plus is here. Memory device is tan's top has the same sign. So the plus here is in your top, the top of your formula. So you remember the other one will be opposite. Just remember the template, and for tan has the same sign on top. So minus will be a minus. So we're going to briefly recap this on Thursday at the very beginning, but then we're going to jump right into more applications of how this works. Okay, so what you're kind of going to start seeing is expressions that look complicated, we're going to be able to rewrite and make easier. Okay, look easier and calculate. Things we can't calculate in one form, we'll be able to calculate by changing the form. So everyone should be completing 7.1 for homework. It's honestly super fast. I would maybe get it out of the way tonight, and then it's done, and you can worry about other subjects tomorrow on your ISU day. If you're coming for the math contest, please come for 8:20, because I have to sign everyone in, you have to fill in your bubble sheets, all that fun stuff. So the earlier, like, be there as promptly as you can so we can start right away after the bell. The sooner you write, the sooner you can go back home. Thanks for listening, guys. Bye-bye.